case. All right. So to go forward, you click on this tab. This is the first chart, but this is really a mathematical file. If you want, you can actually execute things. We start with the three equilibrium equations, two in-plane equilibrium equations in terms of the stress resultants, and the third equilibrium equation in the z direction, which is written now, derived in terms of the moment resultants, mx, my, mxy, and nx, ny, nxy. And these n's and m's are, of course, functions of displacements as well, but there's also explicit displacement derivatives here and here. These are actually nonlinear terms because nx is a function of displacements also, and ny and nxy. So when you have a product of these, this becomes a nonlinear equation. This is our starting point. We actually derive these for an out-of-plane loading of distributed loading of q of xy. So nx, my, nxy, they're all functions of x and y coordinate in general. So is the out-of-plane loading q is a function of x and y. And these x and nx and y and nxy are further related to the displacements to these equations at the bottom. These come from actually the next chart. The next chart shows the constitutive equations between n's and epsilons, strains, mid-plane strains. But mid-plane strains is epsilon x is partial u partial x, epsilon y is partial v partial y, and gamma xy is partial u partial y, partial v partial x. And then the curvatures, second derivatives of the w. Okay? So these equations, the last three equations for nx, ny, and xy, which in fact should be substituted here, come from the next chart, this one, that nx, ny, and xy is equal to a, b, b, d, and epsilon x, epsilon y, and kappa xy and xy. So now these are written in terms of displacements. Curvature are second derivatives of the w displacement. If you put these equations into the top equation in the previous chart, back into these three equations, you get these three equilibrium equations. Three equations, partial differential equations, coupled in terms of u, v, and w displacement. Very complicated. It's very difficult to solve these. So if I take a plate, a rectangular plate, these three equations are the equations that I need to solve for a given out-of-plane loading and some boundary conditions on the w's and in-plane displacements. You can solve the u, v, and w displacements out of these three equations. I don't think I can solve this using my Mathematica unless I go to a finite element method. So what we're going to do is actually start simplifying these three equations. Now note that we are still having these nonlinear terms for nx, ny, and nxy, which are in fact these long expressions that multiply these terms. But I'm not going to be expanding these nx, these nxy, and ny for some time to come. Next chart basically makes the first simplification. We say, let's do cylindrical bending. And what cylindrical bending means, that in short, any partial derivative with respect to y is ignored. There is no variation in any of the displacements in the y direction. So my plate, which is in the xy plane, there is no variation in any of the displacements in the y direction. Only variation is in the x direction, whatever that might be, whether cantilever kind of plate or simply supported plate. But we're going to do cylindrical bending of this plate. We're going to take this plate and we're going to look at what happens if the out-of-plane load bends this into a cylindrical shape. No variation in the y direction. As soon as we implement that condition, any variation with respect to y disappears, and these in fact become ordinary differential equations that and much simpler. This is the x direction equilibrium equation. This is the y direction equilibrium equation, and this is the out of plane. Now, all the other terms disappeared, but my nx is still multiplying this. My q is here, but I'm keeping the B matrix. It's just the coupling between the in-plane stretching and bending. So this is a novelty of this particular problem. That I'm going to actually keep that so that under the action of cylindrical bending, if the plate is also trying to extend or shrink along the length direction, it is allowed to do so. Similar simplification causes the nx to be only a function of x, and y to be only a function of y. And x, not y, x, nothing is a function of y. And xy to be a function of x. And we're not saying that these are zero, and y and xy are zero at this point. They may come out to be zero, but we're not pre-assuming that. Now, I'm making one more assumption beyond this to make it a little bit more simpler. And that is, I'm requiring the laminate to be a balanced laminate, that for every plus angle, there's a minus angle. That does not get rid of some of the B16 terms, but it does get rid of A16 and A26 term. So these three equations, 1, 2, and 3, are going to reduce to these three equations, all three in one line. That the first equation says derivative of a with respect to x of this entire term must be equal to 0. Derivative of this entire term with respect to x must be 0. And second derivative of this term plus nx type times second derivative of this w must be equal to plus q must be equal to 0. And the definition of nx and y and xy also simplified a little bit more. So I'm getting closer to a form that I like to solve, but I'm not there yet. I'm going to make some more simplifications on these. And the next simplification that I do is these A's, B's, and D's are really, in general, not function of the XY coordinate of the laminate. If I have a uniform thickness laminate, no fiber steering, no overlap of the layers, if everything is a straight laminate, then the ABD matrices are constants, which means that I can take them outside the differentiations here. That's on the next chart. That's chart number 4. By taking them out, the first equilibrium equation along the x direction is second derivative of u with respect to x multiplied by a11 minus third derivative of w, b11 must be 0. Equation in the v direction is 0, and out of plane direction is equal to 0. There is not much more simplification in these other than just similar terms. Now, this is still a problem because this is a nonlinear differential equation with the nx. So to eliminate this, we invoke what is commonly termed as product of small terms are even smaller than their individual terms. And if we make the assumption that these terms are small, then we get rid of the term that says this is a nonlinear term. I chop it up off. Now, I can do this if I'm solving static bending solution for small deformations. If the deformations are large, I cannot do this. The NX distribution and this distribution are coupled because NX actually has in it the U displacement and W displacement. So you can see that W0 is already there in NX. If I put this in here, I get nonlinear terms. And nonlinear terms are for large deformations. That's number one. Number two, buckling. Buckling is a phenomena where in-plane loads and out-of-plane deformations are involved. We try to solve a plate, rectangular plate, under, say, compressive loads that we can say determine the buckling load of this panel. That means find the buckling load at which this plate is in equilibrium, and if I if I perturb, it comes back into its original configuration. But this is a problem where NX and W's are really coupled. NX is applying, plate is curving. This problem cannot be, buckling problem cannot be solved by completely ignoring this NX term. In that case, what we do is we take the NX and we turn it into a constant term. We assume that right before buckling, there is an NX value which is constant and is in front of this term. It is computed by this, but it remains constant, that it doesn't, it no longer changes with W. That is, we actually find the NX from the in-plane loads mostly, ignoring the W's, and then use it as a constant load here. So you will see these buckling equations where this out-of-plane equilibrium equation will have NX bar on it. It will mean that it actually is assumed to be constant right before buckling. So by getting rid of this term, now I'm down to these three equations with NX, NY, and XY defined in this particular fashion. Let me see, there's a message in here. No, okay. And I'm almost ready to solve, but I decided to make this a little bit easier. And furthermore, I assumed the V displacement to be 0. This is like a plate. It is not expanding in the y direction. If it does, it's going to be a linear expansion that still can be solved nicely. But I'm going to assume that this plate is between two, say, rigid walls in the y direction, that the V displacement is 0 everywhere. And that will get rid of this term here. And this term here. And that will be these two equations. I also eliminated the equilibrium equation in the V direction. So now I have a coupled U and W equation in terms of the only A11 of the entire A matrix and only D11 of the entire bending matrix and only B11 term of the coupling. So in-plane stretching and bending is coupled. So if the plate bends, I'm no longer assuming the in-plane displacement to be just a direct function of it, but through the stiffness coefficient B11. And this is what we're going to solve today. Okay? And this is, I said, example here. And equation 1 equals A11 U0 double prime of X and minus B11 W triple prime of X equals 0. And equation 2, B11 W as a triple prime of U0 minus D11 4 prime of W is equal to minus Q0. If you remember the beam equation, it's actually pretty close to beam equation that bending times W 4 prime is equal to the load. Okay? But this has other terms. This has coupling term U0, and U0 is also to be solved. So with this, I'm going to open my tutorial and start the tutorial. How is the landing going on? Anything more exciting than bunch of guys like me sitting in front of their computer? No updates. Okay, very good. So tutorial 7, cylindrical bending, will be an interesting one. This executes cleaning up the kernel, quits the kernel. And what I need is also CLT program, because you'll see that I'm going to be using some modules from CLT. I executed the CLT program here. So environment is initialized. Let me make this also to be full screen. My second cell basically repeats the equations that I'm going to be solving these two partial differential equations. It's supposed to break the atmosphere around 348 and land around 355. Okay, very good. We'll keep an eye on that. Let me know if I get carried away and I need to stop right away. Just text me. So we're going to be solving these two equations. So what I showed in the chart, I write the first equation as double prime u of x. This is how you define your equations for differential equation solvers, called dsolve. Okay, this is equation 1 and equation 2. You can see that it has A11 as variable, unknown constant or something, whatever, and has U0, which is the in-plane U displacement in x direction, its second derivative. So these are the two equations. I'm going to be using dsolve of Mathematica and putting question mark dsolve. It says dsolve square equation ux solves a differential equation for the function u with independent variable x. Now I have the two equations, so dsolve opens curly bracket, close curly bracket, equation 1, equation 2 solves in terms of u1 and u2. In my case, it's u0 and w. And if you need more information on this, go to its help, local, and there is ton of examples about how to solve differential equations in Mathematica. For example, this is a differential equation, and so forth. Scope, generalization, a lot of different things in there. This D-solve, by the way, there's also ND-solve. The difference between D-solve and ND-solve is ND-solve solves it numerically. D-solve will actually solve it if it can solve analytically. Okay? And that's why I wanted to simplify my equations as much as possible, because I actually wanted let me close this. Where's my other file? Yeah, I want to solve these equations analytically. So I said solution is equal to D-solve, open curly bracket, equation 1, comma, equation 2, comma. Now here's the thing. If you have boundary conditions, you put them together with your equations. So if you see this curly bracket for equations closes down at the bottom here. So all of these things here have to do with boundary conditions. And I actually wanted to do this in general, that we can solve it in different boundary conditions. In fact, if you look, the first equation is actually for U, it's a second order, so it needs two boundary conditions. The second equation needs three conditions. So these are all conditions that I can think of. But I wrote them all and separated them one with comments. But if I really didn't want to use any of these, I could have just simply done this, get rid of this line, get rid of this line. Get rid of this line because it's basically a boundary condition on W. It's a text. And this is also text. Nothing, doesn't do anything, any computation. And wait a minute, let me erase this. Oh, come on. My cables are causing me problems here. And this doesn't do anything. And this doesn't do anything. This is a more pure form of the following cell that says, okay, solve equation 1 and equation 2 such that W at x equals 0 is equal to 0. Simply support boundary condition at x equals 0. Simply support here. W at L equals 0. Simply support at the other end. At a distance length, limited length L is 0. W double prime of 0 moment here is equal to 0. So it's able to rotate about this edge. And W double prime at L equal to 0 at this edge, able to rotate like that. Then this boundary condition on U, that at x equals 0, U displacement in that direction equal to 0. This doesn't move in the x direction. And I make U prime here to be 0, which actually means strain is 0. Strain in the x direction, U prime, is equal to 0, meaning that this edge can move in its plane direction. Okay. The other boundary conditions that I didn't use, boundary condition second says W is 0 at x equal to 0, L equal to 0. W double prime is equal to 0 at x equals 0. That's simply supported at the left end. But W prime L is equal to 0 at the right hand. So slope at the end here is equal to 0. The third boundary condition is again W at 0 and L equal to 0. There's actually one more condition that you can implement, and that is leaving this edge free. So, but in this case, I'm making W prime at 0 equals 0. No rotation here, no rotation here. You can do one more boundary condition if you like. You can use, not at the same time, but replacing by actually making this one end cantilever and one end free to also move, in which case moment will be 0 and strain will be 0 at that end. So these are the boundary conditions for U. This basically both in plane at x equals 0 and x equals L means R0 for this case, if I use this guy. But by using this star here and making star here, I'm not implementing those. So this is going to actually solve the equations, and it's solving right now. It takes a little bit of time because it's actually solving, as I said, analytically. And here it comes. It says U of x, that is U, mid-plane displacement U super 0x, is S, an analytical form. It has B11 in it, A11 in it, D11 in it, Q0 loading, and it's cubic function of x. W is a function of x, and it's a fourth order function of x, again with ABD terms. If you want to use a different boundary condition, you can maybe try one of these other ones. Say, for example, if you want to use the second boundary condition, then I will take this here, copy, put it here. And if I want to use this boundary condition, I will take that here and put it here. Didn't solve. I must have forgotten something. Syntax expression. X has no closing curly bracket. Where did he lose a curly bracket? Right here. This was the other boundary condition. It looks a little bit more cumbersome in terms of the terms, but bottom line is it's an analytical expression. If it's an analytical expression, I can actually write nice functions out of these. Okay, so I saved the previous solution in here, so I'm going to use that. Basically, it is the solution to this. The first set of boundary conditions that I used. If I take the first term, I get this. If I take the second term of the first, I get this. But I take both solution 1, 2, and solution 2, 2, which is this one and the other solution, and write a new function. I call it U0 field. I put X coordinate in it as a variable. This is a pair matching symbol. Function definition, I take the solution 1 in here and replace the X, which was in here, with X coordinates. So these are two functions that I wrote. So by putting the X coordinates, it will give me the W displacement or the U displacement. So let's take the W displacement and evaluate it at X equals 0, or half along the length, 0.5 L, or at the other end, L. We know the solution to this. W is 0 at 0, W at L equals 0, W at halfway is the largest end in here. U displacement at X equals 0, at halfway along the length of the plate, and at the end of the plate. You can see actually U is 0 at the left end, halfway along the length it has a value, and all the way on the other end even has a bigger value. Now we are ready to use our composites modules to do something. So just to check if I loaded my composites modules, yes I did. Then I can continue. I'm going to use a laminate of 90 degree and 0 degree to demonstrate this. 2 plies, not mid-plane symmetric. Thickness of the fly 0.05 and T35208. With this information, I can immediately go and find my ABD matrices. Okay, so my ABD matrices are actually these. These are just matrices. I can also could have shown this in matrix form. These are the matrix form. But what I need is A11, B11, and D11. So I just use 1, 1, 1, 1, 1, 1 at the end and execute this. These are my A11, B11, D11. If I use L equals 10, Q equals 0, 1, this is the loading. I can look at my field equation for U0 and field equation for my W. This is cubic, and this is fourth order equation, which means I can make a plot of it. And I multiplied the U field by a factor of 10. That's this one, because it's actually much smaller compared to the W value. So the plate is simply supported and bends into this cylindrical form in W. And while it's bending, it's also shrinking in length due to coupling, not because of the geometry. These are small displacements, and because of the geometry, there is no shrinking. Although you can say that, oh yeah, this is bending, so it has to shrink. This displacement U is not because of that, since we are assuming very small displacements. This is actually completely due to the coupling between the U and W displacements. In fact, if you want to see it, I can come back here and make it a 0, 0 layup, which is mid-plane symmetric. This is the A matrix. A1, B1, U field. You see, U field automatically comes out to be 0. So making a plot of the U field, this is what you get. U field is completely zero, and it just bends into this form under uniform Q0 loading. You could have made this Q0 loading to be sinusoidal or stepwise or point load. There are various options for that you can actually use. Let's go back to the coupled matrix again. Let's make it 90 degree. And this is my ABD terms. This is my displacement, and this is my displacements. Now I'm gonna be ready to dive into other analysis. Now I have complete displacement field. So I wrote a little module on the composites called displacement CLT. This is by using the classical lamination theory. It will do something by going from in-plane displacement assumptions to three-dimensional displacements. That is, you know that this place, so far everything is the mid-plane displacements. But this lanyard has a thickness. And as it's bending, the displacements are actually changing through the thickness as well. So question mark CLT will explain what this will do, that given an XY displacement field associated with the midplane, it will compute the displacements as a function of X, Y, and Z and spit it out. So it can be called symbolically. And if you call it symbolically, it will show actually what your assumption was. That displacements are mid-plane displacement minus Z times, that's Z coordinate, times partial W partial X. In this case, Y's are actually zero, so it will become dW dx. And V, this term will be zero because there is no variation with respect to Y. And W is still a function of X and Y. It does not become a function of X, Y, and Z. This is the classical lamination theory assumption. So my X field was like this. If I call my displacement with any of the coordinates defined as a number, it says you can't do this. If it's a number, then you have to provide the U, V, and W fields. So I'm going to be calling the displacement CLT with X coordinate and Z coordinate. As for Y coordinate, I'm going to put 0. And I'm going to put the U field in there, which I already computed, and W field, which I also already computed, and execute this. And this will be displacement field in terms of X coordinate and Z coordinate in matrix form. This is the U displacement field. This is the V displacement field, which is 0. And this is the W displacement field, which is not a function of Z, only a function of X. Okay? So let's take the first displacement field, which is a function of linear function of Z. If I plot this displacement field for Z equals 0 and for a displacement field at Z equals minus the ply thickness, I will see if there is a difference. And I'll make this plot as a function of X along the length of the plate. So I'm going to be looking at the U displacement of this plate in the u direction. Once at the midplane z equals 0, once at the z t ply, which is half lambda thickness above. And this is the plot range. This is the u displacement. So at midplane, u displacement is 0 at this end, but since this plate is bending, rotating, because of the curvature, the top part is rotated, so it has this kind of a deformation along the x direction. This is the x coordinates from 0 to 10 unit long plate. And this is the u displacement at the top. If I took the u displacement also at the bottom and add that to the plot, let's do that real quick. I'm going to put the displacement field 1 at z equals plus t ply. The green line is at the bottom of the plate. Okay? U displacement. All right. The w displacement is not a function of z, so it doesn't change. So I can basically now put this into a menu plate and change my z location between minus t ply and t ply, and make the plot along the plate length from 0 to complete length, and plot this. So this is the u displacement at different z locations that I can choose from here. At z equals minus half thickness, I get this brownish line at the top. If I go this way, I get this green line, which is at the bottom. But note that there is a place in there that u displacement is almost constant everywhere along the length at a certain location through the thickness, z. So along the z direction, I have, and that z direction is 0.0234, okay? It becomes a line. And that's what it says here. Now I'm going to do one more thing, because my z coordinates are typically, now I'm going to rotate this plot a little bit. And what you see here is now a plot of the u displacement as a function of z coordinate at x equals 0. So right at this edge of the plate, I'm looking at the entire displacement field along the thing. It's linear like this, okay? As I go to different locations along the length, let's go to L, what do you think is going to happen? This end is now rotating that way. And the center of this line actually moved in because of the coupling. So I'm going to put this into a menu plate. And now I'm looking at through the thickness distribution as a function of z coordinates of the u displacement at my x. I'm going to do one more thing. I'm going to make, I don't know if you know this trick, but I can actually half length is the in here. Let's say x coordinate. And default is 0.5 L for the x location. So same plot, x coordinate, I'm going to be sliding. And this is 0.5 L, which is 5 units. At the left end, the plate edge is rotated clockwise. If I go towards the right end rotated counterclockwise. Right at halfway along the length, it's straight up and down, and it also moved in by this much. Okay? Now, this is the displacement through the thickness. I can also compute strains from this. I have a module called strain CLT. If you want to look at it, it takes UVW field of the midplane as a function of x and y, and produces as a function of x and z, y and z coordinates of the strain. Strains and displacements are very similar, so they're just going to be, but if you type symbolically, that shows the relationship between u and strain. Epsilon x is partial u, partial x. Partial v, partial y is strain in the v direction. And I'm sorry, I got distracted here for a second. And this is the shear strain in terms of the u's and v's. Again, strains, if you put a number, it doesn't do anything. It needs the field values of user field and VW field. And these are the strain calculations, and in matrix form. Strain in x direction as a function of z. There is no strain in the u direction because I left it free. It's moving in and out. And this is in the what am I looking at? Strain epsilon x, epsilon y is 0, no strain there, and this is that value. You're going to see. Actually, I'm going to make a plot of this first strain at the bottom, at the top, and at midplane. So you can see that strain at the left end is 0, at the right end is equal to 0. But if you are actually evaluating the strain along the length here, it does have a value. Again, I put manipulate in there. 1 minute to atmosphere entry. Okay, I'm going to finish this. And I'm going to let the more exciting things for you to do. This is Z location. And this shows the strain in the X direction as a function of through the thickness location. I can also rotate and do this as a function of Z. And you'll see that this is very similar to, except the strain is going to be 0 at the left end, 0 at the right end, and maximum at 0.5. It will do the same thing for stresses. You can actually look at the stresses as a function of theta z. This is my theta z coordinates. You can execute these yourself. It's a 90 degree and 0 degree layup. Half of it 90, half of it 0. And stress CLT computes the stresses. as a function of z, but note that these are actually piecewise functions, and I can do sigma x plot sigma x, or I can do as a function of z, but you'll see that it actually will make a jump as I'm moving. And if I do plot them as a function of x, you see piecewise stress distribution, how it's changing. Okay, gentlemen, I'm gonna stop here, and you can complete the rest. Now, at this point, you can either drop out and watch yourself. I'm gonna save this, or if you don't have any questions, we'll just go to your own things and watch. But I'm gonna put this on my screen, and unless you have a question, I'm gonna be listening up on the landing here. Why is this not moving?